In this video, we're going to discuss the most important topic relating to energy, conservation of energy. But first, we need to define conservative forces. So a conservative force is when work only depends on the initial and final position. So an example of this would be like the force due to gravity. It only depends on the initial and final position when we're relating the energies. So like gravitational potential energy, for example. And non-conservative force is when work depends on the path that's traveled. So an example of this would be the force due to friction, or a force of like air resistance. We'll say like a resistive force. So for example, like if we have, let's say we have an object like this, and we have this Earth object system. This force due to gravity only depends on the final initial positions when we're relating the potential energies. So this force is conserved within this system. But if we have friction, if something travels from here to here, the force due to friction is going to be less than if you travel in some long path to get from here to here. At every point, there's more and more friction. So the way we can think about the non-conservative forces is that it's losing energy. There's some energy leaving the system by this non-conservative force. And so the big equation that we can define here is that this work done by non-conservative forces equal the change in kinetic energy plus the change in potential energy. So if there's no non-conservative forces, then this will just equal 0. But if there is some non-conservative forces, it'll equal the work due to the non-conservative forces. So this is one big equation here. And so you can think of this work due to the non-conservative forces as energy entering or leaving the system. So let's see how that works in an example. Alright, so we have Bob is 70 kilograms and rides a water slide as shown below. He starts at a height of 50 meters, slides down and reaches a height of 38 meters before coming to rest and sliding back down. If he traveled a total distance of 120 meters, what is the average frictional force on Bob? So in this case, this is his initial height here, which is 50 meters, and he reaches this height of 38 meters when he comes back up, and then he slides back down. So let's list what we have here. So we have the mass, which is 70 kilograms. We have his initial height, which is 50 meters. And so we know what is his initial velocity, right? So we say like he starts sliding down, but we can say that this initial velocity is 0 because he starts and then gravity starts to take him down this hill, right? So he starts from rest. And so that's the initial conditions. And so his final height he reaches is this 38 meters, which notice is less than his initial height. And his velocity final is also going to be 0 because it hits a point of rest before it starts coming back down. And then we know the total distance that he traveled is 120 meters. We want to know the frictional force. Okay, so let's start by drawing our graph of energies. So now we're going to have a kinetic energy initial potential energy, the work from non-conservative forces, and then these final energies. So at the initial point and the final point, these velocities are 0, which means there's going to be no kinetic energy for the initial or the final. But the potential energy starts at some high point of 50 meters and then reaches a final potential energy that's slightly lower but still above the reference point, which we will call the ground to make this easier. So we want to know the work, which must be some negative work that's taking energy away from the system. In this case, that's going to be the friction. So if we start with our work energy equation, we get that the non-conservative forces equal the change of the energies. So we know this kinetic energy is just going to be 0 because the change is 0 because they both are at 0 at the initial and final. But we want to relate these two. So we know the work, non-conservative work, is from friction. And we know this change in gravitational potential energy will just be mass times gravity times the change in height. So we have the change in height. So let's break up this work due to friction. So that'll be the force due to friction times the distance times cosine of theta equals mg, and I'll write this as hf minus h initial. And so this cosine theta is going to just go to 1, because at every single point that he's traveling, the force of friction is perpendicular to the motion he's traveling in the opposite direction, so this will actually be -1. And so now we can pretty much rearrange this equation and solve for the force that the average frictional force here. So if we set this and divide by the distance, we can get the frictional force. And so now we can just plug in the numbers that were given and solve for the frictional force. So these are the change in heights over the distance, which is 120. And so this frictional force that was applied on average is 68.6 newtons. Alright, so let's go over when we can apply conservation of energy. So the main idea here is that the mechanical energy equals the kinetic energy plus the gravitational potential energy. That's the total energy. So if the work from non-conservative forces equals 0, then the change in mechanical energy will also equal 0. And so that means, using the equation from before, we'll have 0 equals the change in the kinetic plus the change of gravitational, and we'll get this kinetic energy initial plus the initial potential energy equals the final kinetic energy plus the final gravitational potential energy. And so when we have this situation, we can call this a closed system. And that means all the energy will be conserved and no non-conservative work is done. And you should note that energy is always conserved overall, but sometimes it'll leave the system as the form of like heat energy or thermal energy. It could also leave as like chemical energy or electrical or sound. So a lot of ways you can lose energy, but if energy is conserved in the closed system, then we won't have any loss of energy outside the system, and it will only be transferred between kinetic and potential. So let's see how that works with a final example here. So we have Bob jumps off a trampoline into a foam pit. He leaves the trampoline at a velocity of 5 meters per second up and lands with a velocity of 7 meters per second. How far did he fall below the trampoline, assuming the air resistance is negligible? Okay. So we're given the initial and final velocities. And note that since we're dealing with scalars and energy, we don't really care the direction that he's falling versus jumping. That's the nice thing about energy versus kinematics. In kinematics, you have to be really careful about your directions, but with energy, since we're dealing with all scalars, it doesn't really matter. It's just how the speed that he's traveling for the energy. So we want to know, what was this height that he fell? Because he's on the trampoline, right? He's jumping on there, and he jumps up and then falls down a certain height, and that's the height that we want to find. Alright, so if we write out our energy graphs for a conserved system, we only care about these initial and finals. So we could put the non-conservative work here, but we know it's going to be 0 because we've defined this as a closed system, making the system Bob and the Earth. So he's going to have some initial, I'll do this in a different color, he'll have some initial kinetic energy. He'll also have some initial potential energy. And then we know he'll have some final kinetic energy because he lands with 7 meters per second. But if we define the ground or the foam pit as the potential energy equaling 0, that's the reference point, then there'll be 0 potential energy at the end. And so all of this initial potential energy is converted to kinetic energy, and that's how we can find the height. So let's start with our equation. We have the kinetic energy initial plus the gravitational initial equals the kinetic energy final plus the gravitational final, should say final. So we know this is going to be 0 because we just defined this as the reference. So now we can turn all of these into their equations. So we have 1/2 mass velocity initial squared plus mg. In this case, we'll say h because that's the height that we want to find, and the final, which is 1/2 mvf squared. So now we have all these variables, but we don't have the mass. But notice that mass in this case just cancels out. And so I'm also going to multiply by 2 to the whole equation to get rid of all the fractions. So we just have v naught squared plus 2gh equals vf squared. And so now we can move our equation around to solve for h. Should be minus here. And so we can rearrange for h equaling to vf squared minus v naught squared over 2 times the gravity. And so if we plug in the variables that we were given, we would get a height of 1.22 meters, and so that's how far he would fall. Alright, so the main thing about the energy is if we can define it as conserved, there's no work done outside of the system, so all the energy is just going to be transferred around between kinetic and potential, and that's the main idea, and that's how you can use that to solve a lot of problems. And notice we could solve this with kinetics, or not kinetics, kinematic equations, and we could use our initial and final and use an equation and have gravity, and that's all fine, but usually energy is a little bit easier because you're only dealing with scalars and it only depends on the initial and final positions, which is really nice. So alright, leave any questions you have in the comments, and thanks for watching.